Morning, everyone. Because I have a lot to cover, I'm just starting a stopwatch so I don't miss anything. So today I'll be talking about Java and containers, how to make it awesome. Initially, I thought I had a different topic, title for this topic. Optimize your Java applications, containerize and optimize your Java applications in a cloud-native environment and deploy them to Kubernetes. But I thought that would be buzzword bingo, so I thought just keep it this. So just a little bit of myself. I'm the community maintainer of the Docker images at Adopt Open JDK. And I'm also the OpenJ9 cloud optimization architect as well. So today it is partly slides and also a demo. I'll be just, all of the Docker files and YAML files and so on are in this repo. So if you want to take a look at them later, you can take a look at that as well. So before I start, I thought I'll just quickly ask people, so how many of you here have already containerized your applications? Okay, a few hands. And how many of you are using Java 8 in your containers? Or just using Java 8? That's most. So Java 11? Anybody looking at beyond 11? Okay. Anybody below 8? Okay, nobody. That's good. So I thought I'll just start with what is Adopt Open JDK. So anybody here already aware of Adopt Open JDK using the Adopt Open JDK binaries? Okay. So Adopt Open JDK is a community which helps you provide pre-built OpenJDK binaries, and it consists of the build scripts and the infrastructure, where we pull from the OpenJDK sources, build from there, and do a lot of testing. And we have extensive Jenkins setup over there, and publish the binaries. So these are downloadable, and you have REST APIs. And of course, the Docker images are available over there. I'm sure that this picture is already out of date. There are many more companies that are actually supporting this initiative, and these are available across all of these different architectures. So I think this would be a good place to start if you are wanting to containerize your Java applications. The Docker images, would be a good start. So what I wanted to do today was to just walk through the normal cycle, assuming that we are all Java developers here, application developers. So what would be the normal cycle of a Java application developer? What are the different stages? And look at each and every stage and look at how we can optimize that stage for, if you want to run your application in a containerized environment. So the first thing would obviously be the build. So you made some code changes, you've done a commit, and now what? So you want to generate a Docker image, and I'm sure you would have heard about this quite a bit. You want to make sure that your Docker image is as small as possible. So why is this a requirement? I work from the IBM Bangalore office, and sometimes I deploy to the IBM cloud, which happens to be in Dallas. And sometimes the network speeds are so bad that if I have a big Docker image of, let's say, 1 GB in size, it might even take me 40 minutes to do an upload. You don't want to be having something, you don't want to be doing that when you're deploying your applications, especially when there is a agile process and you're doing several hundred commits a day and so on. So you want to be able to have small images and keep the time that it takes for you to push your images to the repos or provision and deploy them in a Kubernetes cluster, for example, as shortly as possible. So there are a number of ways in which you can actually reduce the size of the image. One is the Alpine Linux. So you can, if you don't know about that, you can check that out. It just is 5 MB in size versus 80 MB or so for Ubuntu. It just has muscle libc and busybox. There are a number of slim images that we provide as well at Adopt OpenJDK and even the regular OpenJDK as well. So you can, these are stripped down images where, which probably have things taken out, like, from the GRE itself, things like desktop and, sound and things like that, which you probably don't use in a typical server-side application. So I thought at this point it'd be nice to actually walk you through a Docker file and some of the best practices about how to make sure that your Docker image is really small in size. So here's an example Docker file. Again, this is from the same repo that I just mentioned earlier. So you can take a look at these Docker files as well. So the first thing would be that I'm starting off with so this is a two-stage Docker file, and the first stage is the build stage, and the second one is the one which gets actually packaged and gets run in a in a Kubernetes cluster, for example. So these are optimized for two different things and for different purposes. You might be aware that Docker has layers, and so each and every statement here corresponds to a different layer. And it actually helps you to, the layering actually helps because it caches each and every layer, and if there is no change in a particular layer, it doesn't need to build it again. So we can take advantage of that and create as many layers as we want in the build stage. However, when it comes to the packaged runtime layer, the runtime image, which is the second half of the Docker image, starting from this from statement here. So we want this to be optimized for runtime. We don't want too many layers at runtime. It might add file system overheads and cause performance issues and things like that. So you want to make sure that the number of layers in the second half of the Docker file is as small as possible, and the first half can be as many as you want, because you're optimizing for your faster build cycle. So the first thing you'll notice is that I'm starting with the Maven Docker image here. That's again a good practice not to install any of your build tools locally on your systems anymore, because once you install, let's say, a Maven or a Gradle, you would tend not to upgrade them, for example, and keep it at lower versions, and it might lead to disparity between developers having different versions and things like that. So having a standardized Docker file where you have a specific version of Maven put in there is the best practice, because that will ensure that all the developers are using the same level of Maven, and these are maintained by somebody else. Like, for example, Adopt OpenJDK. At Adopt OpenJDK, we provide the Maven, and we maintain the Maven Docker images as well. So it's as easy as just downloading these images and making use of them. And of course, the next thing is that you can install all of the tools that you want, a typical developer would want, and which Java developer doesn't use Vim, right? So that's obviously has to be there. And then you do a git clone and get your repo. So this is not necessarily the right, the only way to do it. So you could have a local git clone that you're mounting into your during the Docker build as well. But this is a easier, cleaner way, because this encapsulates the entire sources inside your container and make sure that you can do a build. And you notice that I have split the Maven commands into two layers. So the first one is where you do the install all the dependencies and copy them over locally into the container. You do want to make sure that these two things are separated out, the packaging and the dependency that is So this ensures that once you build the container for the first time, it downloads all of the dependencies, and then subsequently, if you have issues with your code and you have to recompile multiple times, you're not having to download all the time. And we all know that Maven tends to download the internet every time you run that. Okay, now that you've come all the way to packaging it, so you can now pick a new starting point, which is in this particular case I'm using adopt Open JDK 8 GRE Open J9. So here obviously I just need the GRE. I don't need Maven and all the other build tools. So I'm starting from that point. And the next thing you'll see here is that I'm creating a user. So one of the issues that we have is with Docker especially is that if you by default you are the root user inside the container. So and obviously that's not a good thing at all, especially because Docker happens to have a daemon, and if you have a malicious program that makes use of a vulnerability and becomes root inside of a container, you are effectively root on the entire system as well. So you could become root on the system as well. So you want to make sure that your application containers, the actual runtime ones, are don't have the root privileges. So the best practice is to create a user within the Docker file and switch over to become that user and do the rest of the operations as part of that user. And of course, the next thing is that you copy over from the previous stage all of the packaging that you're done. And so now you have a much more optimal Docker image that gets generated. So this one is with Java 8. But there are a few more things that you can do with Java 11. So I have here another Docker file in the same repo. So the top part remains mostly the same until we get to the jlink command. So obviously you might be aware that you can actually reduce or create your own custom GRE for your application from Java 11 onwards. And jlink is the command that helps you to do that. So one thing to note here, though, is that you don't have to modularize your application to take advantage of this. In fact, this particular application that I have is not modularized, but I can still take advantage of the jlink to give me a GRE that includes only the modules that my application needs. So I've mentioned all of the specific modules that that I would need. The advantage with modularization is that I don't need to specify them this way. I would have to manually figure this out and put it into this jlink command. If I had if I had modularized it, all I had need to do was just run this jdeps inside and point it to the jar file from the the last time that we looked at, and that would automatically pull in all of the modules that your application needs. But because I have not modularized this application, I'm having to manually specify all of the modules as indicated here. So the java.desktop, instrument, logging, and so on. The other thing is that you can actually exclude all of the files that you typically don't tend to use, which are all packaged inside the JRE. Things like debugging and dat files and some properties and font files and things like that. So of course, if you ask me to debug in that Docker container, that's a different story altogether. But this is really good from a runtime perspective, that you're reducing the security exposure and the attack surface, and making sure that you're packaging only the stuff that you need right from the operating system, the Java, as well as the application. The next thing to look at here is, we have something called as share class caches. So all the stuff that I mentioned So I have Docker files for both Hotspot and for OpenJ9. So you can take a look at them there. But shared class cache is actually an OpenJ9 only specific feature. So shared class cache is something that allows you to take in ahead of time compiled code, the AOT code. So what, how do we generate that is basically by actually running the application. So if you see here, I'm specifying the share class cache command line, and then I'm actually running the application within the Docker file. So when I run the application with these specific -x options, it creates a share class cache, which is essentially the bytecode that has been compiled and put into a physical file on the disk, which is what we call as the share class cache. And so this helps in terms of startup. It actually helps about improve the startup by about 40%. Because you already have compiled code to start off with. Even though this is not the most optimal code, it is pretty good enough for you to be able to get a better startup and then optimize as you go forward. One thing that you do need to remember is that you need to run the application on the target machine where you expect to run this application. The problem otherwise would be that, let's say, for example, I run it on my laptop, which is very different from the server where I'll be running my application. Totally different set of optimizations might apply there. So it's always better to run this particular step on the machine where you actually would end up running the application. So this is so if you look at it, this is actually better off in a pipeline where in a Jenkins pipeline or something like that, where you run the application, generate the cache, and then use that to create a new Docker image. But I've just illustrated how to create that using this two-stage Docker file here. The second, in the second half, so here this time I'm starting with Alpine instead of the GRE. So as I mentioned earlier, I don't need the full GRE or the JDK. It's only the generated GRE that would be needed. So in this case, I can take advantage of that and use Alpine as a basis, which is just 5 MB in size. But because Adopt Open JDK provides binaries that are compiled with glibc and not muscle libc, which is what is available in Alpine, I do need to install glibc within Alpine. So I have a custom version, and the Docker file for this is available in the repo as well. So I start with that 3.10 version of Alpine, install glibc on top of that, and do the same set of steps that I did earlier, except that this time when I copy over the application code, it's also copying over the GRE that was generated, the custom GRE, as well as the shared class cache. So this together generates not only a really small image, but also make sure that we get good startup time. So let me actually run this and check the sizes. So you can see that the J-linked one is actually the smallest one. It's about 89 MB in size. With the shared class cache, which adds about 30 MB, it becomes 121 MB, but it is still small enough. So to get that additional startup benefit, you need to add that the AOT code, and that takes up over 30 MB in size. But that still doesn't. I mean, that's still reasonable enough, I would say, for a typical Java application. So this has the operating system, the custom GRE, the application, and all of its dependencies packaged together. So if I now run this application, so just for comparison purposes, I'll just run the J-linked version first. Okay, so let's look at how long it took for it to start up. The first message printed here, 8:35:13, and so it took about 3 seconds for it to start up. So now let's run the same thing with the share class cache built in. So this, as you can see, it took about 2 seconds. So it starts at 41. Okay. 8:35:41 and 8:35:43. So it took about 2 seconds. So typically you get a 40% benefit. I mean, this was of course a pretty simple application, but the larger the application, the more classes that you have, the more benefit that you can get out of this. So just to make sure that we have it actually running, let me run the application. I can access it from localhost 8080. So this is just a sample application that uses the Watson APIs for text-to-speech. Say,
hello from EclipseCon.
Okay, so okay, so I think the last thing I wanted to mention when it comes to Docker files is the fat jar and the hollow jar concept. Again, this is something that people are talking a lot about recently. I'm currently using a Spring application, and that's not so good when it comes to providing what is called as a hollow jar. A hollow jar is just the bare minimal app server that can run by itself, and without all of the application and dependencies packaged together. The reason why you want to have a hollow jar is because of the same Docker file layering that I mentioned. So if you have the hollow jar as a different layer, when you do the copy over here, you copy the hollow jar first. That is a layer that typically never changes or changes very rarely, and the application layer, on the other hand, changes more often. So you want to take advantage of the Docker file layering concept, make sure that you have create a hollow jar in your Maven, and then copy that over as a different layer, and that helps you to actually reduce your Docker upload times as well. Okay, so there are, of course, lots of other tools that can help you to generate the same thing. Things like Gib, and we also have now something called as Rhapsody from IBM that takes away all of this complexity, and you don't have to worry about all of doing all of this stuff manually. So Rhapsody is a tool that helps you to actually create the most optimal Docker file and generate the Docker images for you. So I do, ask. You can take a look at it when you're free. Okay, so moving on. So now that you have created the most optimal size of the Docker image, and of course the startup part as well. So I think I've already covered this. So using the share class cache, it allows you to get the best startup, or reduces the startup by about 40%. There's another mode here, which is the quick start. You can use that if it's a short running application. Things like serverless use cases probably would be a good fit. But if your application is a long running one and you're worried about throughput, X quick start probably is not so good. Okay, so we have now an application that is starting. You saw how quickly it started. It still took about a couple of seconds. But what if you want instant startup? And in fact, serverless is something that expects you to start really, really quickly. Maybe sub-second. And CRIU I found is a tool that is very useful in that particular regard. CRIU is checkpoint restart in user space. It's a Linux project. I would ask you to check that out. It's really nice. It's an open source project built by the Linux community, and what it allows you to do is bring up an application. So once you bring up the application and it starts, for example, the top bar at the bar at the top. So that's the normal startup time of the application. So um, once the application comes up, you can do a checkpoint. So what a checkpoint is essentially taking the contents of the application in memory and dumping it to disk. So you take a checkpoint and dump all of the memory contents onto disk. Now you can create a Docker image out of that and commit the Docker image. So now when you run the Docker image, we run CRIU restore internally. So the restore is nothing but just copying the contents of the disk back into memory, and it appears as if the application started up instantly. So usually the restore takes something like 200 milliseconds, or it depends on the size of the application. For really small applications, it takes up something like 10 to 15 milliseconds. For maybe really large ones, it might take up to 100 milliseconds or so. So that's a huge advantage. In fact, we tried this with Jenkins. Jenkins typically takes about 20 seconds or more, depending on the number of slaves and things like that. But using CRIU, we can bring up a Jenkins server in something like 120 milliseconds. And the best part is that once you create that container, you can have as many instances as you want. And this whole thing can be encapsulated within a Docker container. So you start your application, checkpoint it, create a Docker container out of it in a pipeline, and then when you deploy it to a Kubernetes cluster, it comes up instantly. So this is something that is really useful. And the best part is that unlike all of the other frameworks like Quarkus and things like that, this is just Java, and you don't there are no limitations as such. And this can be equally applied whether it is Java, Node.js, or any other runtime as well. Okay, so now that we have an application running and it is scaled up to how many instances you want, what's the next step? So we want to make sure that running container gets the most out of the server that it is running on. So there have been a number of changes in the JVM itself to make sure that you get, the JVM is container aware, and all of the limits that have been imposed on it. For example, Kubernetes has this -- request and -- limit, which says that the container cannot go beyond a certain limit. So I think the JVM right now is in a much better place to handle all of this complexity. And if there's really one thing that you want to take away from this entire talk, I would suggest that it be about the -XX max RAM percentage. So how many of you here use -XMX in your Java applications? Okay, lots of hands going up. So that I would say that that's something that we need to avoid inside of a container. And the reason for that is illustrated here. So typically in a Kubernetes cluster, you'd have different set of limits depending on where you're running your application. You can have a different limit imposed on your container if it's in a dev QA cluster versus in a production cluster versus in some other place. And so what would happen is that, so let's say, for example, these are the 3 examples there. So in the first case, we have the container memory limit set to 2 GB. And in the second case, we have the limit set to 3, and in the third case, we have the limit set to 4 GB. If you have hard-coded -XMX to 2 GB, in the first case, it is possible that you might actually end up ooming, because remember, this is just the heap, and the entire container memory is limited to 2 GB. So there are native code and other aspects that might push up the actual usage. So you might end up getting your container killed. Whereas in this case, you have lots more memory allocated to your container, but you're not able to use it because you've set the value of -XMX or hard-coded it. So what's a better way to do it is actually use the -xx max RAM percentage. So max RAM percentage is, as the name suggests, a percentage of the limit that has been imposed. So if you're running it on a bare metal system with no containers, it just looks at the overall RAM and then uses that as the percentage. Inside of a container, if a limit has been set, then it uses that limit as the overall RAM that is available to it, and then uses the percentage to calculate the heap. So in the as indicated here inside the box, in the first case it would be 1.6 GB and 2.4 and 3.2 and so on. So it automatically expands and contracts as as the size that has been imposed on it. So I would suggest that please use the -xx max RAM percentage and initial RAM percentage instead of XMX and XMS. There are more details about this in the blog down there as well. So this brings to a question of how do you size your container? So this is a question that is that's a big problem for the developer. So when I deploy my application, what should be the right size for my container? How do I determine that? And not only that, the problem here is that the sizes might change. We are putting in lots and lots of commits every single day. So if I size the container today, that might not be valid tomorrow because of all the changes that have gone in. Maybe I need more CPU, or maybe less, or maybe more memory, and so on. So the question is, how do you optimize, or how do you find the optimal size of the container? So we actually, I'm really pleased to announce the launching of the tool called Cruise. We just open sourced this last week. It's available for free. You can try this out. So what you have to do is download this and deploy this in your cluster, and this can actually monitor all your applications and provide recommendations. So I have it running here. So here's the GitHub repo, github.com/cruise, and so the way that it provides the recommendations is using a Grafana dashboard. So it uses internally Prometheus to grab all of the metrics from the applications that are running, and then you can choose the application that you want to monitor. So for example, I choose the namespace inside Kubernetes cluster and my specific application, and it gives me the recommendations for that. So these were the values on the left were the values that were deployed with originally, and the values in yellow or orange are the ones that are the recommended values as seen by Cruise. So here you can see how these values changed over time. So the dotted lines are the recommendations, the CPU at the top and the memory at the bottom. So you can see the values changing based on the actual workload and the actual incoming load. So as an IT administrator, you can take a look at this, and if you feel comfortable with the limits that have been recommended here, you can use that to actually deploy it in your cluster. So right now that part is not automated as yet, but we plan to do that in subsequent releases where you can automate it based on a confidence factor, for example. Okay, so I think I have just one more minute, so let me quickly cover the other aspect of deploying to a cloud, especially in the public cloud, is that you have you're paying for resources that the container is using, and if your application is sitting idle, you don't want to be paying for those. So actually in Open J9 there is an option called -xx idle tuning GC on idle that allows it to be, and this is in fact turned on by default. So this what this does is that figures out if the application is idle and automatically releases all of the free memory that it is not using back to the operating system. So you're actually paying less if you're being billed on the amount of resources that you're using. And the last thing that I have is about debugging. So it's not very easy, especially because of if I remember in the first stage we tried and stripped away everything, And so now it makes it a lot more difficult for you to be debugging in containers. So one thing that we do have, I mean, this one is the OpenJ9 Diagnostic MX Bean. I think on Hotspot it's called just the Diagnostic MX Bean, so it's available there as well. So you can actually use this, connect to a running application inside of a container using JConsole, for example, and then trigger a dump. So this doesn't require you to restart your container or add in special options and things like that. So your container is running, you can connect to it, and then trigger a dump using just from JConsole itself. Okay, so we also have something called as a Java core, where where the application, I mean, so this when you do a dump, it gives you information about the running application. So we have added additional fields in there to determine whether or not the application was running in a container, and also about any limits that were imposed on the container, so that it helps you when you're debugging as well. Okay, so yeah, that's all I had. So we covered all of the different stages that a typical developer would go through, and looked at each of them to see how it can be optimized from a container perspective. There are a number of links that, the application that the demo application and all the Docker files, you can get it from the first link. Cruise is the tool that helps you to right size and optimize your container. And then CRIU, which is the open source version, the open source community actually that helps you to checkpoint and restart. I just wanted to point out that for the same application, I have demonstrated in this repo a set of scripts that allow you to do the checkpointing and restarting as well. So, and if you want to deploy to a cluster, any additional privileges that you need can be encapsulated in a RBAC So we have all of the files here if you want to take a look at it, and how to checkpoint and restart your application. You should be able to do that with this. Okay, so that's all I had. Thank you.